In this video we are covering joint life and last survivor functions from contingencies in actuarial mathematics. In the next video I will be covering joint life and last survivor assurances, annuities and reserves. So this video I'm covering the basics and foundations and understanding that underlies a lot of this stuff and that you will probably have to use in tests and exams to calculate probabilities or to manipulate results or to prove something. And then in the next video I'm going to be covering the types of things that you need to actually answer questions in terms of like pricing questions and reserving questions. Okay, so the underlying assumption that we will have throughout this section, joint life and last survivor functions, is that the two lives that are being considered are going to be independent. Okay, so maybe let me quickly explain what exactly is a joint life or last survivor function. Okay, so far we've only been dealing with one life. That is, we've been dealing with probabilities of an individual life surviving to certain points, dying at certain points, and assurances and annuities for that life. But now we are dealing with joint life functions. So where the probabilities I'm now going to be looking at is when both of them might die within a certain time, or maybe how long until the last one of them dies, or that type of thing. And then assurances and annuities also for that. So it'll pay while at least one of them is alive, or maybe it'll pay until the first one dies, or maybe it'll pay from the time that the first one dies until the second one dies, and you don't know who's going to die first or second. So this is the types of things that we deal with these joint lives. Okay, so let's start off with the most basic thing, and that is TXY, the complete future lifetime, the complete joint future lifetime of the two lives now aged X and Y, should be equal to the minimum of Tx and Ty. So all this is then is the lifespan of the shortest of the lifespan of the person who dies first, okay, out of lives X and Y. So if X dies first, then Txy will be Tx. If Y dies first, Txy will be Ty. Okay, so this is a joint lifetime. Okay, then we also have a cumulative distribution function for this, a CDF, f Txy, where Txy is now my random variable for time t. This is just using different notation, is Txy less than or equal to t. So the probability that either of the lives will die before time t. And this will be equal to 1 minus the probability that either of the lives survives longer than time t. But since we said that these lives are independent, this is the same thing as saying the probability that life X survives longer than time t times by the probability that life Y survives longer than time t. Okay, so just now writing this in notation that we're familiar with, this is 1 t px t py. Okay, so this is my CDF. I also have a PDF for my joint lifetime, and this is f Txy t, which is just then going to be the derivative of this. So we then say the derivative with respect to t of 1 minus tpx tpy. Okay, so when you expand this out, what happens is the derivative of this is a constant, so derivative of 1 is 0, and then the derivative of this, we have to use the product rule. So it'll be the derivative of this times by this plus the derivative of this times by this, and all of this multiplied by a negative. Now, a result that you should remember from one of the previous videos is that the derivative of TPX is equal to negative TPX mu x plus t. Okay, so if you follow that logic, it's not that complicated, and do the steps that I've said, expand it all out, what you arrive at is TPX TPY into mu x plus t plus mu y plus t. Okay, so this is the joint PDF, or the PDF of the joint lifetime. Okay, then let's define this probability as well. And this probability in words is defined as the probability that either life X or life Y lives, that both life X and life Y live longer than t years. Okay, so this is because XY here, the status here, is the joint lifetime. So I want one of these statuses, either X or Y dying, so one of these statuses failing should happen after time t. Okay, so the first one to fail, which means that this joint status fails, should happen after time t. Okay, so this equals to TPX TPY. Okay, so just the product of the two because they're independent. Okay, and then that is just Lx plus t over Lx times by Ly plus t over Ly, and then in actuarial notation then Lx plus t times Ly plus t is Lx plus t with a colon separating the two statuses, Lx plus t, y plus t. So then similarly Lx, y. Now I don't have to use the status here, I mean the colon in between those two, because it's quite obvious. But if I have x plus t and y plus t, I've obviously got to use the colon to separate the two. Or if I had numbers here, I would also have to use the colon, because otherwise it might just look like one long number. Okay, so that's fair enough. So basically I'm saying that Lx times Ly is equal to Lxy. Okay, and I'm also saying that TPXY is equal to the product of those two. Okay, then dxy, this is just a lot of definitions here, quite boring, but we've got to do it. So Lxy, the number that are alive now, aged xy, minus the number that will be alive in 1 year's time. Okay, now what this essentially means, dxy, is the number of these pairs that will fail within the next year. So where one of them will die within the next year. So if I have 5 pairs of people, I have 10 people, and they're each in their individual couples, then I say in the next year, if 3 of them die and 3 of them were all from separate couples, then my dxy would be 3. Okay, but if I said 3 of them died, 2 of them were from the same couple, and 1 of them is from another couple, then my dxy here is just 2, because my Lx plus 1, y plus 1 would be 8. So if this is 10, then my if the 2 die that are in the same couple, and then the other one dies from another couple, then only 2 of these couples have failed. Okay, so then it's 2 people have failed here. So this here is 8 now. So that means that these failed couples is 2 of them. Okay, now when I'm talking about failed, I'm just saying that failed in terms of the status, the joint status. So their joint status, xy, has failed in that either x or y has died. Okay, now we also have qxy, and this is, as you'd probably guess, dxy Lxy. Okay, now we also have, defining this, mu x plus t, y plus t is equal to minus 1 over Lx plus t, y plus t, times by the derivative in terms of t of Lx plus t, y plus t. Okay, and this is a very similar formula that we had for just mu x. Okay, we would have had Lx in here, Lx plus t in here, and Lx plus t in here. Okay, and then that would have been mu x plus t. Okay, so very similar formula. Now, this, we can actually expand this, or actually just change this. So this takes a very similar form to the derivative of the natural log of Lx plus t. So if you think about it, the derivative of the natural log of t, or let's say the natural log of some function of t, will just be equal to that function in the denominator times by the derivative of that function in the numerator, which is exactly this here. So we convert this into negative times by ln of Lx plus t, and then what happens is from there we can further expand and differentiate and do some things there, and then what we eventually end up with is mu x plus t. Okay, now I've skipped it because I don't want to waste your time just doing proofs the whole video. I want to try and get the understanding across, but you do need to know these things. So just because I'm skipping over it doesn't mean it's unimportant. It means that it's unimportant for me to convey understanding. Okay. All right, now kxy is just the integer part of txy. So that's just the floor of txy, which is the same as the Curtate future lifetime of a life aged x, say, is the same as the floor of the complete future lifetime. So same idea going on here. Okay. Then the probability that the Curtate joint lifetime is equal to k. In other words, this joint status fails between time k and k plus 1. This equals to k deferred qxy. Okay, so why is that? Because it means kxy, when there's a hidden implicit 1 over here, means that the status must die within a year, and then that probability is deferred by k years, so between time k and k plus 1. Okay, now that's the joint statuses mostly covered, or statuses, I don't know how to say it. That's joint statuses mostly covered. Now, let's talk about these last survivor statuses. Okay, so t, x, y with a line on top. So you'll recall that I explained assurances and annuities that had stuff like this, where there are two statuses in this subscript. What essentially the way that we interpret this is, this assurance pays out, it's a term assurance, this term assurance for n years pays out when x, the status x, fails before the time n, these n periods run out. Okay, so if x fails first, which is why this line is on here, then it pays out on the death. Okay, that's when it pays out. So that's what it's basically specifying. Then something like an annuity xn is saying that this annuity will pay in arrears yearly until either this time runs out, it's a temporary annuity, or until the life dies. Okay, so I'm dealing with two statuses. Now similarly, I'm dealing with two statuses here. So over here, my statuses for something like here with a complete joint future lifetime, what I was saying then was when either of them fail. Okay, but when I put the bar on top here, it's basically inverting that and saying when the last one of these statuses fail. Okay, so then instead of txy, which was the minimum of tx and ty, txy with a line on top is the max of tx and ty. So it's saying that if x survives longer than y, then this complete last survivor future lifetime is going to be tx. Okay. So this Similarly, it also has a CDF, so let's write that out. So ftxy with the line on top there, t is equal to the probability that txy is less than or equal to t, which is equal to tqxy. Okay, so those are all notational things. And now the important thing here is that this equals to tqx times by tqy. Okay, so earlier we had that tpxy is equal to tpx times by tpy. And we interpret this as saying that the probability that both lives, x and y, survive beyond t years is the probability that each individual one must survive beyond t years. Okay, now this we interpret as the probability that both of them die within the next t years is the probability, just the probability that each individual one dies within the next years. Okay, now please note that this line on top here allows us to calculate that. Okay, without this line on top here allows us to calculate that. So if I add that line on there, that is no longer true. And if I take away that line there, that is no longer true. Okay, so please take careful note that it's the last survivor for these death probabilities that allow us to equate those two, and it's the joint life status for survival probabilities that allows us to equate those two. Very important distinction, and you really do need to remember that. Okay, now if I interpreted this tpxy as being the probability that both x and y survive beyond t years, then how would I interpret tpxy like that? Well, what this is saying then is that I'm dealing with a last survivor status. So the last survivor status means that the last one to die, that last one to die should be after time t. So this is saying that at least one of them lives longer than t years. The probability that at least one of the lives live longer than t years. This is the probability that both of them live longer than t years. This is the probability that the last one, with this line on top, the last one dies within the next years. So in other words, both of them die within the next years. And then tqxy is the probability that the first of them, this joint thing, dies within t years. So it doesn't matter necessarily what happens to the second life. We're only concerned with what happens to the first life to die, whether that be x or y. Okay, so think of these xy, these joint statuses as being, or statuses, or however the hell you say it, think of those joint ones as being the first one to have a certain event occur. So the first life to die, so, or the first life, or one of the lives must survive. The first one to die must be after time t. Okay, the first one to die must be before time t. Here, the last one to die, I'm saying because of q, must be before times t. Okay, the last one to die before times t. Here, the last one to die must be after time t. Okay. So I hope that is as clear as it can be. I hope I didn't make a mistake, because I tried to say all that pretty quickly. But if you didn't catch on, or you think I said something confusing, just leave it in the comments and I'll tend to it, okay? And I'll make sure that I hash it all out and make sure that everything makes sense. I think I said it correctly, but you never know. So just, if something seems peculiar, let me know in the comments and I'll tend to it. Okay, then, where do we go from here? Okay, so if I'm writing this CDF of the last survivor future lifetime, I can write that as that, but I can also write it as such. 1 minus TPX plus 1 minus TPY and then minus 1 minus t px t py, which also equals to 1 minus tpx minus tpy plus tpxy. Okay. So what that then is ft x t plus f ty t minus f t xy t. Okay, so these steps are not so important. It's more important that I've arrived at this final thing. Okay, so this is a very crucial result. A function of this last survivor future lifetime is equal to the CDF of the single life status plus the CDF of the other single life status minus the joint life status. Okay, so in general, when we are dealing with any function that's dealing with our last survivor life status, you'll see this come up to be true time and time again when we're dealing with the last survivor statuses. What I have then is the last survivor equals the single plus the single minus the joint. Remember this, it is very important and it's very helpful for you to remember formulae. It really is very helpful, and it also applies, doesn't just apply for the CDFs, it applies for the PDFs, and it applies for many other things as well. So this is really important. It applies for probabilities, obviously applies for probabilities because that's what my CDFs are. So these things are really important to remember this particular formula here. Okay, so I'm going to put an exclamation mark there. Really important. Make sure you remember that. Okay. Now, similarly to how kxy was the integer part of txy, kxy with the bar on top, so the last survivor curtate future lifetime is the floor of this here. Okay, nothing peculiar going on. And then this probability that kxy equals k will equal to k deferred qx. So remember, if I have the probability that kx is equal to k, what that then equals to is k deferred qx. Okay, so why is that? Because the probability that this life-aged x must have a curtate future lifetime being k years means they die between time k and k plus 1, which means I have kx there with that hidden 1, implying that they die within a year, and then that year being deferred by k years. Okay, so that's how that works. Now, this comes back to this formula here, and I take it, the deferred probability of death for a life-aged x plus that deferred probability for a life now y minus that there, minus the joint. Okay, so you'll see then single plus single minus joint. It comes up very, very often. All right. Now, TP XY has 3 different formulae that I encourage you to remember and to remember how to interpret. So first of all, you probably would have guessed it. It's the single plus the other single minus the joint. Okay, let's interpret this as well so that we have some intuitive base why this last survivor equals single plus single minus joint. So think about this here. This is the probability that the last person to die is after time t. Okay, so what I then need is the probability that this one survives longer than there, plus the probability that this one survives longer than there. But that means if I just add those two up, it means that they must both survive longer. Okay, if I'm just dealing with TPX and TPY, I'm only dealing with them independently. So it doesn't really make sense. And I would then have to multiply. So it really doesn't make sense there. So what I then have to do is subtract this double counting. So think of it like this. This is like X, and this is Y, and this intersection here is XY. Okay, so if I need XY, which is all of these, then if I just take X and then I add Y, then I've double counted that middle area. Okay, so I've got to remove it once over here. Okay, so that might give you another little intuitive base to try and understand this. Okay, another way to interpret this, another formula, is 1 minus TPX times by TPY plus 1 minus TPY times by TPX plus TPX TPY. Okay, so let's think about this. So this event here is equal to the probability that one of them dies, but the other one survives for both instances. So here I've just invert the X and the Y to here. So X dies within T, but Y survives. Here, Y dies within T years, but X survives, or they can both survive. So this here is the probability that the last one must die after time T. So the last one to die must happen after time T. So that means that either one of them could be alive, or both of them can still be alive, which means that the last one will die after time T. Okay. Then another formula, which is probably the go-to, the one that you should try first, is this one here. 1 minus TQXY. Last survivor there. Okay. Simple enough. Then another thing we have is TXY plus TXY with a line equals TX plus TY. Well, why is that? Well, this is the minimum of TX and TY. This is the maximum of TX and TY. So whichever one is the minimum won't be the maximum. So if this one is TX, then this one has to be TY. If this one is TY, then this one has to be TX. So they have to equal to left and right hand side, you have to be equal. Same thing applies for for K.